All right, so I've handed back the test. The scores are in Moodle. Have a look at that and be sure that.
Thanks, kid.
Yeah, it's pretty good. Okay, now what we got here is a static grade calculator, if you like, okay? This is just an Excel spreadsheet. You could download this thing. Will it let me do this? I guess we'll find out. Is that something? No, it's not much. Okay. Click. Okay, I'll click that. Untitled. Google Chrome. So if you go into this thing, you can figure out about where you are in the class if you're interested in that. Okay. Where's this stupid thing? Assessment. Where am I? Grade sheets. Why did I do this?
There's a status folder in there.
Yeah, I got too many things in there, obviously. Here we go. All right. When you open, is already open. Reopening will cause any change. Yeah, that's okay. We'll do that. All right. So this thing looks a little bit like that. It's not very complicated. And remove the files. Yeah, we can remove those. So 200%, will that work? Okay, there we go. All right, so it looks like this. So if you open this thing, what you do is you just put your scores in here at the top. So typically if people are turning in all their homework, they get about a 95 on the homework. Let's say things, frankly didn't go very well. So let's say we got a 62 and a 58, and we want to know, what do I got to do to pass the class? Okay, you can put different numbers in there for the final, and then you can see what will happen there. Hang on here. Oh, I got a 92. Okay, let's say you just get a C on the final. What's going to happen there? And let's make sure I got the right formula in there. Yeah, I do. Okay, good. Okay, so remember, I use two systems to figure out your grade, okay? And I take the one that works out the best, and that's what you get. Okay, so here's method 1 and method 2. So the only thing you change is the line at the top. So you can put different numbers in here for your final. It'll calculate both methods and give you both scores. So if you get a 73 on the final, you'll get a 69.8 with method number 2, and that'll round up to a C. Okay. So that's one thing I want to point out. The other thing I want to point out is, the system of grading I use is fairly forgiving. I mean, I curve a bit as I did on this. And also I have that one system where I count the final exam more than the other tests. So, you've got to, even if you've busted a test, you still have a shot, pretty good shot at getting through the class, okay. But you do have to do, perform well enough on the final to do that, of course, okay. So this is something you can play around with. You can enter in your 2 midterm scores. Your homework, that percentage is good on Moodle. Now, and then you've got your 2 midterm scores. Keep in mind the Moodle course total is meaningless. It doesn't mean anything. It's an auto-generated number by Moodle. It does not account for different grading systems. I can't really get Moodle to do this, to use 2 different systems and use a logic routine and pick out the higher of the 2. It's not something I can do. So, you can, so don't pay any attention to those Moodle course totals. They don't mean anything, okay? Just use this spreadsheet if you're curious about your grade. So this can get you some idea where you're at, okay? All right. And we'll probably go over that test maybe in a little detail tomorrow. The first one was a resultant, so you had to just use those methods that you had used for finding a resultant. Although I didn't take much off if you treated it like equilibrium. I mean, they're pretty much just mirror images of each other anyway. It's not that big of a deal. The second one was kind of what I frankly warned you about, was doing the trigonometry on that one angled arm, taking a moment about A and figuring out the reaction at C. C actually made a 9-degree angle with the horizontal. Third one was a truss. You had to find the reactions first and then just do the standard truss methods. The one after that was a section. You cut through that one panel of the truss, took a moment. The easiest way to do it was use the right-hand side of the truss. Take a moment about that point down at the bottom. G, is it? Yeah, take a moment about G. That was the quick way to do that. Then you could solve for FDF directly by cutting vertically through that one panel of the truss and taking a moment about G. The zero forces on that other truss were up, let's see, PDF annotator. Get that. Okay, that other truss, I don't have, well, I guess I do have a copy with me, but what that thing looked like was something like that. And then we had other little details going on with this thing, of course. What do we have going on with this thing? That comes down. And we had one of these. Back up, down, there we go. Something like that. And then we had these little things going on here. And then we had a load right up top there and another load over here. Those are both zero. That's an unloaded corner. Those are unloaded T, so they're zero. Once they're removed, this becomes an unloaded T. So there are the zeros on that thing. And then the last one there, the easiest way would be to take a moment about the z-axis, because you've got A and B right on the z-axis. That isolates DE. So a moment about the z-axis would get that for you. You could also use vectors and take a moment about A or about B. That would get the unknowns down far enough to solve. The idea on that is you got to take a moment about some point that has unknowns on it. That way you eliminate those unknowns and then can solve for the remaining unknowns that you want to find. If you have questions on this, we go over it in a little bit more detail tomorrow, but that's the quick story on that one. Okay. We got any questions on that thing? All right, let's see. Let's go here, and then we'll go here. Okay, we got a couple other things to get through here. We did the centroids and such. That was last week on Wednesday. And now we've got another what's called a shape property that we want to work with here. It's called moment of inertia. And I don't know if you've covered this in physics yet or not. There are a couple different types of moment of inertia, so you should know that. The first type is an area moment of inertia, and that's what we're going to do. There's also something called a mass moment of inertia, which is quite similar, as the names suggest, but it's a little different property, okay? So let's have a look here. All right, so an area moment of inertia is a property of a beam that kind of helps it resist bending, you might say. Whereas an area moment of inertia, or excuse me, a mass moment of inertia is something that's used to quantify how well a beam would resist angular or excuse me, not a beam, but a shape would resist, or a part or some object would resist angular acceleration about a given axis. So we're going to look at the area moment of inertia, which is more particular to this kind of engineering. In physics, you're probably looking at the mass moment of inertia, would be my guess, when you get to that.
So area moment of inertia is more of a type of resilience, where mass moment of inertia is more of a rigid body.
Well, area moment of inertia, I mean, I think of them in terms of what they represent and why we use them. Area moment of inertia I use when I'm designing a beam, because it'll help me determine part of the description of how well a beam will resist bending, which is quite often what we want to do. Okay, if you have a beam, a floor joist, which is a beam under a floor, you don't want the floor to bounce when people walk across it, obviously. You want it to be more rigid than that. So the area, how the amount of area in the beam and how that area is oriented influences that. Whereas the mass moment of inertia, you don't just look at the area, you consider the mass of an object. And what you get from the mass moment of inertia is the tendency of this object to resist angular acceleration when you apply a moment to it, okay? So they're different, they're calculated in very similar ways, but they describe a little different properties, okay? So why don't I ask you a couple obvious questions here. These beams under a floor, they're called joists. Which floor joist do you suppose would have the least bending? I think the bottom, yeah. I think we're usually pretty good on that because the bottom are bigger, and when in doubt about designing something, make it bigger, right? Because it'll resist force better if it's bigger. Now let's have the same area, same size beams, but let's orient them differently. And which floor joist do you suppose would have the least bending this time? One would hope the top, right? Because we've got it oriented, got those beams oriented with a long axis faces the top. So as that load pushes down on the beams, the long axis of the beam that way is resisting it, okay? Now that's the common sense end of it, and I think that's pretty apparent there. Now, of course, we're engineers, so we want to take that common sense and quantify it and calculate it and do all that kind of stuff. So a moment of inertia is a calculation. It's a shape property of a beam that describes those two things I just went over. Area, and not only area, but a certain way of orienting the area so that that shape would not bend, okay? So the moment of inertia, the definition for I sub x, now we describe this by the axis of bending, the axis about which you're going to bend around, so if I'm calling out I sub x, the definition of that is the integral, which means to add up y squared, a distance, times a series of small areas called dA. So we could put a bunch of little dAs in there above and below that axis, and each one will have its own specific y distance. Square the distance, multiply it by the area, do that for the entire shape, add everything up, and you get the moment of inertia. So notice the two factors that create a large moment of inertia are the area, and that's pretty obvious because that makes the dA go up quite a bit. As your area increases, so does your dA, but also the distance of the area from an axis. So both things are factors in the moment of inertia. Now the units of moment of inertia are length to the 4, so they're kind of a funny unit. And also, they do indicate that this is a little bit abstract. A centroid, you can point to a particular point on an object and say that is the centroid, but you can't do that for moment of inertia. Moment of inertia is more of a concept. It's not really a thing you can look at and obviously see in a beam, not like a centroid. Okay?
So moment of inertia is the inertia isn't pegged. You also need to have a material strength to go with that.
Yeah, if you want to
know how it's going to actually behave.
Right.
Okay.
Yeah, moment of inertia is part of the situation, not the entire situation. As you say, the strength of the material also indicates how much a beam will bend to. So we're good with that? Okay. All right, now when a beam bends, it bends about what's called the neutral axis. The neutral axis runs down the middle of the beam, okay? Now when a beam bends, what happens then is above the neutral axis, you have compression. Below the neutral axis, you have tension. And I've just got a phone book here that I'm using to represent a beam. Notice what happens when I bend the phone book. Notice with the phone book, I've got a binding on the left, loose pages on the right. The binding kind of represents what happens there with an actual beam. The pages you can think of as being sheets of atoms that are bonded together. And look what happens to those pages. If you hold them together as you do with the binding on the left, you get a nice right angle, which is the same angle you started with before you start to bend the beam. But on the right, you see what those pages want to do. They want to slide across each other. On the top, they'll slide outward, whereas on the bottom, they slide inward. The reason is, when you have this circular bending, or whatever kind of curve that is, as you get further and further away, you get a bigger and bigger sector of the circle, a bigger distance to traverse before, as you hold that given angle of bending, okay? So what's happening here is there's a given angle of bending here, and we could call that whatever you want, theta. To keep that constant theta, this distance that I'm outlining on the bottom has to be longer than the one on the top, right? So the net result of that is that when this book bends, you've got one line right in the middle, and that's called the neutral axis, that exactly fits the angle. Whereas the lines on the top, the pages spread outside of the angle, and the lines on the bottom, the pages pull in from the angle. Okay. Now what a beam's going to do, see these pages, if you think of them as sheets of atoms, the pages themselves are stuck together because you've got bonds between the sheets of atoms. So the beam's going to say, well, you can't slide in. I'm not going to let you do that. I'm going to pull you out. And similarly on the top, the beam's going to tell those atoms, or whatever you want to call them, you can't go out like that. I'm going to push you in. I got to hold my structure together, because if a beam starts having things sliding across each other, it's broken, okay? It's failed. So the beam holds itself together. So on the top, it has to pull in a little bit, and that's compression. On the bottom, it's got to stretch out a little bit, and that's tension. So that's what happens to a beam when you load it and it bends. On the top, you get compression because it's got to pull itself in. On the bottom, you get tension. It's got to pull itself out, because a beam holds that right angle. See, that's what a beam does to keep its structural integrity together, to hold together. Okay? If it can't do that, it's failed. It's broken. Okay? So y'all good with that? So the neutral axis has neither tension or compression. In this case, above the neutral axis, we got compression, and the bottom, we got tension. Okay? All right, so that neutral axis is the neutral line. It actually is applied along the length of the beam, even though we find it on the centroid of the beam, on the cross-sectional area of the beam. The neutral axis runs through the centroid on the cross-sectional area of the beam. We apply it down the length of the beam. That's what we do. Okay. So when we find this moment of inertia for a beam, typically what we do is we find it about the neutral axis is typically what we do. Okay. All right, if you're going to make a structural beam, what you want to have is a high moment of inertia while using a small amount of material. Okay? You want as much moment of inertia as you can get because that helps you resist bending for the smallest amount of material you can use, because using a small amount of material lowers the cost and the weight of the beam. Okay? So what types of shapes do they end up using for moment of inertia to get a good moment of inertia? Keep in mind that I sub x is just an integral, which just means to add up the distance squared times the area. So what you want to do there to maximize your moment of inertia is maximize the area, but we don't want to do that anymore than we have to because that adds weight and cost. What we really want to do is focus right there and use that area efficiently. So what type of shape uses that area efficiently? An I-beam, yeah. Okay, so that's why they've come up with that, okay? So back at around the turn of the century, when they're, a little later into the, I don't know how late this went, but pretty good ways into the century, like when they were building the Empire State Building, what they did, they used standard shape beams, okay? Those were the standard of the day, and that's obviously why they're called standards, okay? So what the deal is there is, if you load these up, they're very strong in the Y direction, because what you've done there, you've put most of the material out away from the neutral axis. You've maximized that Y part of the equation. Okay, this thing up here is called a flange, and connecting the flanges is the web, okay? So you try and put a lot of that material in the flange, and that gets you good strength there, and if you set the flange a long distance away from the neutral axis. The web really just serves as a way of connecting the two flanges together. Okay. So that was the standard of the day for a long time, but then codes started to change. And I think you can particularly see this in the Northwest, because what a standard beam is designed to do is to take a vertical load. It's good at that. But it's not very good on a sideways load because it's quite narrow. Sideways loads, if you want to give them a fancy name, you call them lateral loads. What sort of lateral loads are we going to have here in the Northwest at some point? Earthquake, yeah. So standards don't work very well, okay?
No, the lateral load apply to or wouldn't that still be reasonably good because it's got the long, flange?
Yeah, sure. It's got the flange sticking out either way, but that's enhanced in the current beams that are commonly used now in the wide flanges. The flanges are bigger, they're beefier, and they're wider, so they resist lateral loads better. So these are the standard beams that are used today. Now you can still get standards. There's miscellaneous beams that are used. They're actually a category of beam. There's also a type of I-beam called a heavy pile, which is just a pile that's driven into the ground, like for foundations, for bridges and things like that, and even for buildings sometimes too. They take I-beams and cut them in half and make them into T's, cut them in half the other way, you get channels. Also, another thing that's used are pipes and tubes. A nice trick there, you see a few of these around campus here and there. They take a pipe or a tube and fill it with concrete, because concrete's a lot cheaper. That'll stiffen it up a good bit too. Okay. So these are some of the common structural shapes, and you'll see they're all have pretty good moments of inertia. Okay. Okay. There's an I column there, an I beam right there. Here's the standard floor joist of the day, TGI, that's called. Used to be just 2x they'd use, but now they use these TGIs. They're TGI, right? And they're They're cheaper, lighter, easier to handle, and stronger, okay? There's a tube used for a column. Here's a, not sure if that's a single T or a double T, but that's a big old concrete beam. That's what this campus is made out of, the roofing at least. Okay. So there's some applications of those shapes, okay? Now, I-beams have callouts on them. The callout starts with a letter that indicates what type of beam it is. The next number is the depth. That's a nominal depth, which means it's not an exact measurement. It's an approximate measurement used to describe a category. So W36s are I-beams that are about 36 inches deep. They might be 34, 35, 36, 37, somewhere in there. They don't manufacture them all to be exactly 36, but they're all about 36. So they group them together and call them W36s. And then the weight per foot is 300 pounds per foot. Designers want to know that number because it's a big part of the load that they're designing for. Okay. All right, so we want to be able to calculate this. And we can start off where we could figure out the moment of inertia of a rectangular beam. Okay. Now, when you do this, you set up a differential area that runs parallel to the axis. Okay, because what you do is you name the moment of inertia and you calculate the moment of inertia about a given axis. So the differential is parallel to the axis. So that if we're going to find I sub x here, I bar sub x, which means the moment of inertia of a beam about a centroid, about an x-axis running through the centroid. So I guess that would be the way to say that. What we're going to do then is we're going to use that basic definition y squared dA. So what we've got here is a typical rectangle with a base B and a height h. We're going to use the centroidal axis, so we're set in the middle, h over 2 and h over 2. Okay. So let's see what we got here. We're going to measure up a distance y and find the area. Take the square of y and multiply it by the area. So what's the area there? It's the base times dy. Okay. We're going to start at the lower limit. That would be negative h over 2 from where our axis is, and end at our upper limit, which is a positive h over 2. So there's all the information there to run the integral. So we measure up a distance y, find the area, b times dy, and run that starting at negative h over 2 and end it at positive h over 2. So then we just do a little bit of calculus here. So we got the integral of y squared dA. Y squared is just y, that distance we're measuring, squared. The area will be the base of the rectangle times dy. And we're going to start at negative h over 2, and we'll finish at positive h over 2. So that's what we're up to. Okay. And the rest of it is just running the calculus there, kind of step by step. Okay. So the integral of, I'll pull the b out because it's a constant. So b times the integral of y squared dy. And what? That'll be y cubed over 3, right? Because the integral is an antiderivative. So y cubed over 3, plug in the upper limit, h over 2, subtract off the plug-in for the lower limit, negative h over 2. You're cubing those, so it's h cubed over 8 minus a negative h cubed over 8. I pulled that factor of 3 out in front also, so it's b over 3 times h cubed over 8 minus a negative h cubed over 8. And then we just got to work with our fractions here. So we get b over 3 times 2h cubed over 8. The 2 and the 8, you can simplify that to just h cubed over 4 times b over 3, it's bh cubed over 12. So there you go, there's the moment of inertia for a rectangle about its centroidal axis. And that's on your formula sheet, that's a standard formula. So when you look at finding these moments of inertia, you look at the shape, but you also have to know what axis you're calculating it about. Okay, so the location of the axis influences the number. So, you know, a good bit of messing around there with a little bit with the calculus, most of it just with the algebra to get everything combined, but we get to bh cubed over 12. Any questions on that? All right. Now, down at the bottom of that page, we can find the moment of inertia of a rectangle about its own base this time. Okay? So it's the same run of numbers there. The only difference is the limits. If we're going to find the moment of inertia of a rectangle about its own base, we're starting at 0 and we're going up to a height of h. Now, the rest of it's the same. You got y squared dA, you got y squared b dy, and you integrate that and get y cubed over 3. But notice that you, when you find the moment of inertia for that shape, being as we've changed the axis, we also really changed the value. Instead of bh cubed over 12, it comes out to be bh cubed over 3. Okay. Okay. So, all right, now, I'm showing you some calculus there, but I think when you're working, you're probably going to use tables a good bit for the doing of this. And there's standard moments of inertia for standard shapes. The common ones are a rectangle, which we just mentioned is bh cubed over 12. For a triangle, it's bh cubed over 36. For a circular circle, it's pi r4 over 4. And for a quarter circle, it's 0.05488 r to the 4. And these are all moments of inertia about the centroidal axes. Okay? So if I want to find the moment of inertia of a rectangle, and let's say this is 2 and 3, if I want I sub x, what am I going to get out of that? So I got bh cubed over 12, I got 2, 3 cubed over 12, right? So what do I got there? I've got, what is that? Is that 4.5 when you get that all worked out? 2754 over 12? 4.5, okay. And if that were inches, I didn't really spec units on that, it'd be inches to the 4. Now, let's say I want to find I sub y. What would I get then? Now the base is parallel to the axis, okay? Yeah, it's 3 for the base now. Even though that's really a height, I would just call it the base. I would define the base as being parallel to the axis. The height, which is I would define as being perpendicular to the axis, becomes 2 cubed over 12. Is it 2? Is that what we got? Oh, right, yeah, it comes out to be 2 inches to the 4, okay? You okay with that? You can kind of just switch the definition of B and H as needed. I would define the base as being parallel to the axis and the height as being perpendicular to the axis. Some people will say that the I sub y for a rectangle is HB cubed over 12, you know, however you want to look at it.
So are these all on the blue sheet?
Yeah, those, actually that copy's taken right off your blue sheet. You get the 4 of them, run right across. It's on the right-hand side.
If you have an ellipsoid, does that?
If you have an ellipsoid, I don't have one for an ellipsoid. You know, you could look it up, I'm sure, if you needed it. Okay. Now, what we're going to get into, and maybe we'll have time tomorrow, we do have homework due Wednesday, we'll cover it tomorrow, of course. But if we have time, we'll get more into this moment of inertia. We're going to look at when you start building composite shapes. So if you have like a T-beam like that, you're going to run into a little trouble with these tables because the tables give you only the centroidal moment of inertia. Obviously, they can't give you every possible moment of inertia. So what you get off the tables are the centroidal moment of inertia. And then you use something called the transfer axis theorem to calculate a moment of inertia other than a centroidal moment of inertia. And this comes up a lot when you build composite shapes. You know, you get different rectangles you put together to make T-beams or I-beams or whatever. All the centroid of each rectangle is not on the neutral axis of the object. So you have to use the transfer axis theorem to kind of work through that, okay? All right, so I think that'll pretty well do it for today. So tomorrow we'll go over that homework, plus if we have time, we'll cover some new stuff, okay? The homework